So I'm Steve Applin. I'm the head of the data department at European XFEL, where we do amazing science with the world's most powerful X-ray laser. So we fire lasers from over there behind me, and they come all the way from Daisy, and they come about 3.5 kilometers, and then they land downstairs. We're standing right on top of the hall here, and they arrive with megahertz. So we've got megahertz X-rays turning up. And what I do, is oversee all the data components of that. So I try to understand what the requirements are from the scientists, from the leading scientists that we have here, and we bring the tech, that is detectors, that is electronics, that is control systems, that's IT infrastructure, that's one of the things we're talking about today, but it's also the data analysis. And the data analysis is taking the information that we get in raw bytes and bits and converting that into scientific information that people can take away and analyze at the universities or the other institutes and produce scientific papers, which is knowledge. That's our export product is the petabytes and petabytes of data that the scientists condense down into knowledge. I started this journey in 2010, and we talked about the amount of data that was going to be generated at this institution. And we did some back of the envelope calculations, and we could see that it was going to be up to petabytes per day. That was 2010, and we took a deep breath, and we really didn't understand how we were going to able to take petabytes per day of scientifically valuable information and storage there. So we have to capture that data in real time. We have to be able to then store it. Any of our scientists take measurements here, and they publish it in Nature. They would be delighted if we get a Nature paper. So not only do we have to capture the data, we also have to be able to store it for up to 10 years. That's generally the gold standard of scientific best practice, is keeping the raw data for 10 years. And we're talking about petabytes and petabytes of data. So storage is one of our key problems to solve. Now, for the archive, we do that on tape. So we can't afford to put all of that onto the IBM hardware, which we buy, which is absolutely exceptional hardware. But we wouldn't want to have that standing around. It wouldn't be even efficient from a financial point of view. It also wouldn't be efficient from a sustainability point of view, but also from a space point of view. One of the major challenges we have at the moment, and always really will, is capturing the data of this 1 megapixel cameras. I remember getting a call saying, Steve, why do you want to spend that much money on the storage for a 1 megapixel camera? And I had to explain to our procurement department, this was not a webcam. This was a 10 million euro investment in an X-ray detector, 1 megapixel camera. And we were going to have several of these. Now, they put this stuff out at megahertz, and we need to be able to capture that. That's a lot of data. We're talking about gigabytes tens of gigabytes per second. Yeah, and we need to capture that in real time. And what's really important when they're doing the experiments, we need to be able to analyze the data when the experiments are happening. So we need to be able to do this in real time. So we have to be analyzing the data at the same time as the data is coming in. But in the near time, within minutes, hours, overnight, we need to be able to turn that analysis around into a full-scale analysis. So we have to run over petabytes of data. We need to put that into the compute cluster. So I/O, it's not just the capacity. We're not just looking at the capacity, we're also looking at I/O. If we don't have the right I/O values, then we can have the best computing cluster in the world, but we're data limited. We're not CPU bound, we're I/O bound. That's something we have to focus on. That's another one of our key specifications. Of course, this is why we use combined solutions, where we use the fastest amount of read-write that we can get. Typically, we're going to silicon. We're not with spinning disks there. But for integrity, we of course cannot afford to lose this data. So we do need redundancy, we do need parity disks, we do need all of those things further down. So we have an accelerator here which is 3.5 kilometers from the source. So the accelerator produces electrons, they fly down the tunnel, and then they produce photons, X-rays, which then we detect here downstairs. So that converts that. We have these detectors, X-ray detectors. That then goes into the data acquisition system. We take it into the data acquisition system. We do some online analysis, but it actually goes back. So our big compute center is 3.5 kilometers behind me. So back at Daisy. So I always say, they send electrons, we send photons back, right? Through the optic fibers, which go exactly the same direction through the tunnel. So what we need is we need a tiered storage system. So we have to have something here in real time. We need latencies less than a second on megahertz data. So we need to be doing that in real time. So we have a storage cluster here, which is connected to what we call our online storage. So that has to be very, very fast. It doesn't necessarily have to be particularly deep. And the tiered system we have at the back. So that's at the Daisy Computing Center. So we have the online storage. So the online storage, there we're looking for the capacity in terms of I/O, right? So we really need to turn that around quickly. The other thing with the online storage is it has to function as the buffer. So it's the buffer for the high performance computing cluster and the GPU cluster that we have right next door here to be able to do the detector calibration. That has to happen for the scientists downstairs who are watching it to do it in real time. But at the same time, we need to drain that off because the data is continually coming. So that's why we need this tiered system. Online here, offline back at 3.5 kilometers away. That's a key criteria. So redundancy is key. I do not want to walk downstairs now after getting a phone call to say, sorry guys, you have to stop this experiment because the storage is not working. That can't happen. So it has to be a highly redundant system, which is failure safe. I also don't want to walk downstairs and say we lost the last hours of worth of data. So it's incredibly important to us that we capture this data. It's incredibly important that we store it. We could pack it away and say don't touch it, and then it'll probably be safe. But it has to be used. It's constantly used. It is extremely valuable. The data on that storage is basically our export product. One of the things that makes us keep coming back to IBM is because we have a long and trusted partnership in working on these solutions. This is not just about the kit. It's about working together to find solutions as we evolve as an organization. That was right back at the beginning. I can't really put a value on that partnership. We have a technical solution, fine. It's changed. We went from the 8.6 system, x86 system, through to the PowerPC. That's a different system. Fine, we don't need to worry about that. Why we keep working with IBM, why we keep investing in IBM hardware, is because it keeps providing us solutions that are reliable, that we trust, and we have a partner that we work with. The response rate is great, I have to say. I'm very, very happy with that. When something doesn't work, it gets fixed. When we need something brought through in production, it happens. We've managed to when we started off this project, we dropped 2 systems onto the beamlines at Petra, into the computing center. They came off the factory in Mexico as series number 001 for one system, and the other system was also serial number 001. They may not keep this bit in the edit, but let's see. While we were setting those up and commissioning, everything was fine, and then one day, everything crashed. I ended up with some very excited managers phoning me. Fine. It's commissioning, it's a prototype, we're setting it up. We had that system back up in 2 days. You cannot do that on your own. We could have never done that on our own. That's why we want a partner who provides us with a warranty, who provides us with support, who provides us with an opportunity to take a solution to its edge. It was always fun working with the IBM guys because they used to turn up and say, I'm not sure we could tweak the system quite like this if we were one of our corporate clients. But you guys have a different risk profile. That's one of the things I always think that we offer to IBM. I've asked, why do we keep going back to IBM? The question is, why do IBM keep coming back to us? That's also a valuable question. I hope that we continue to be a partner where we can develop solutions, we can drive those solutions to a point that they are not normally deployed. They are highly complex systems with massive amounts of parameters. Olaf, who's been with us for a long time, tweaks amazing things. He makes the systems run in ways that probably it would make a Formula One engineer's eyes open. That's a partnership. We work together, we take the risk. We know if you drive these systems to where we want them, they may fail. It's not if they will fail, but what happens when they fail that's important to me.